Welcome to this explainer. If you've ever looked at modern AI in production and thought, man, this feels like massive overkill, kind of like firing up a multi-million-dollar supercomputer just to figure out how to turn on a light bulb, well, you absolutely aren't alone. Today, we're diving into a brilliant new architecture that completely rethinks how we use large language models. Instead of treating LLMs as these universal calculators where every single repetitive query burns through massive compute, this framework treats them as just-in-time compilers. It's a totally new way of looking at neural execution, and the implications for raw speed, operational costs, and enterprise-grade safety, they are absolutely enormous. So here's our roadmap for today. 1. Decoupling AI reasoning. 2. The System Zero architecture. 3. The 16-byte imprint. 4. Bulletproof bitwise safety. 5. The compilation lifecycle. And finally, 6. The AI optional paradigm. All right, let's jump right into section 1. Decoupling AI reasoning and moving from calculators to compilers. Think about it. Right now, in most architectures, a neural network is essentially acting as an incredibly expensive lookup table. Imagine hiring a team of advanced mathematics PhDs and forcing them to sit in a tiny room all day just to sort your daily junk mail. I mean, that's basically what we do when we ask a massive billion-parameter model to decode a routine command, route a standard API call, or parse basic user intent over and over and over again. It is incredibly wasteful. You're using an unfathomably complex probabilistic engine to predict an outcome that is already firmly encoded in the input. Decoupling reasoning from execution means we stop asking the AI to guess what a user wants every single time, and we start saving that brilliant intelligence for when it's actually needed. In the current state of things, the LLM does absolutely everything. It parses the text, it reasons through the logic, it executes the command. It's exhausted, and honestly, it's slow. But the new state introduces a just-in-time, or JIT, compiler concept. If you ask the system to learn a new skill, it thinks about it exactly once. It uses all that incredible LLM reasoning power to solve the problem, sure, but then it compiles that thought into a hard-coded deterministic rule. The next time that exact same skill is needed, absolutely no thinking required. The AI doesn't even need to be consulted. The system just acts, running the compiled code instantly. Moving right along to section 2, the System Zero architecture. Let's see how this actually looks in the tech stack. To make this JIT compiler concept a reality, the system splits operations into 3 distinct layers. System 2 is your LLM. That's the heavy, slow, brilliant brain, invoked only for high-level planning or handling totally unknown tasks. Then we step down to System 1, the semantic router. This uses lightweight embeddings, which are essentially incredibly quick mathematical guesses, to figure out what the user's intent might be. But here is the kicker. System 1 has zero authority to actually run anything on your machine. And finally, we get to System 0, the deterministic runtime. Think of System 0 as the strict bouncer at the door of your hardware. It handles hashes, opcodes, and capabilities with absolutely no reasoning involved whatsoever. System 1 might ask what a user means, but System 0 actually authorizes the execution. This is a huge relief for developers because it means the unpredictable LLM is never, ever the root of trust in your application. If you're familiar with operating systems, think of waking up the LLM like a page fault. In a regular computer, a page fault happens when the system suddenly has to go fetch data from the slow hard drive because it wasn't readily available in the ultra-fast memory. It is a massive performance hit. Well, in this new AI architecture, invoking the LLM is that slow, expensive fallback. You only want to pay that heavy compute toll and endure that latency when it's an absolute emergency or a brand new task that the system has literally never seen before. Everything else gets handled instantly by the fast memory of System 0. Let's dive into Section 3, the 16-byte imprint. This is the core executable innovation. 228 bits. Normally, teaching an AI a new trick means tweaking billions of neural network weights in a process called fine-tuning. That process costs an absolute fortune, takes hours or days, and often leads to something called catastrophic forgetting, which is where the AI successfully learns the new trick but suddenly forgets how to do basic math or follow simple instructions. It's frustrating. But this architecture, it abandons that brittle process entirely. Instead of modifying weights, it writes the new skill down into a hyper-efficient 128-bit structure. Let's actually break down those 128 bits. It packs everything perfectly like a tiny optimized suitcase. You have 16 bits for the symbol, 16 bits combined for the skill and schema, and 40 bits to tell the system the exact memory offset and native operation to run. Then you have 24 bits dedicated entirely to state flags and strict capability permissions, and finally 32 bits for provenance, which is essentially the cryptographic history of who or what created this skill. This 128-bit or 16-byte C-struct is a direct execution descriptor. And here is why that specific size is literal hardware poetry. Exactly 4 of these 16-byte records fit perfectly into a single 64-byte CPU cache line. That means the processor can use SIMD operations, essentially doing math on an entire row of data simultaneously in a single clock cycle. It is brutally, beautifully fast.
Okay, Section 4, Bulletproof Bitwise Safety. We're redefining AI security right down at the hardware level.
Right now, we rely on prompt safety. We use fragile English, literally begging the AI, please don't delete my files. And as we all know, clever prompt injections, like simply telling the AI to ignore previous instructions, can easily trick the model into doing catastrophic damage. We are trusting core enterprise logic to a system that can be defeated by a polite request. That is insane. This architecture introduces bitwise safety. By putting capability flags directly into that 16-byte imprint we just talked about, System 0 enforces safety using brutal mathematical bit masking. If the imprint says 00000000 and a 0000000001, that means it only has permission to read the file system. If a malicious prompt tricks the LLM into trying to write or delete a file, the hardware simply looks at the bit mask, sees it doesn't match, and drops the execution instantly. No fragile English, no hallucinated policies, no reasoning required. Just instant, unbypassable hardware-level rejection. Which brings us to Section 5, the compilation lifecycle. How does a new skill actually get safely learned? So if the LLM is locked out and System 0 is locked down, what's the process? It requires a strict, self-optimizing lifecycle. First, when an unknown input arrives, the LLM is put in a sandbox environment. It can propose a workflow or an execution graph, but it absolutely cannot touch the real world. Next, that proposal hits a validated schema, which is a checkpoint that ensures no hallucinated data types slip through. Everything must be perfect. Third, it is cryptographically signed, so we get a permanent audit trail of exactly who or what approved this new skill. Corporate compliance departments are going to absolutely love this. Only when it passes all of this scrutiny does it become an active imprint. It gets reasoned out once, heavily scrutinized, and then bypasses neural inference forever after. And finally, Section 6, the AI optional paradigm, the deterministic offline bombshell. Because the system acts as a compiler, you can deploy it in 2 different ways. The semantic runtime uses the pure runtime but keeps a tiny embedding encoder and a local LLM attached for when a totally new request comes in. But here is the bombshell. You can also ship just the pure runtime. This is a 100% offline deterministic execution engine using only hashes, symbolic matchers, and those 16-byte imprints. Absolutely no AI model is required to run it. For fields like aerospace, embedded systems, or high-frequency trading, industries that traditionally cannot use generative AI because it is just too unpredictable and hallucination-prone, you can now deploy a highly capable compiled system that has 0 unpredictability. It proves this is a deterministic execution engine where the AI is entirely optional at runtime. I'll leave you with this provocative thought. Once the heavy thinking is done, and those skills are successfully compiled into brilliant 16-byte hardware-aligned imprints, do we even need the AI present to run the application? The future of AI applications might just be running flawlessly, deterministically, and safely without the active AI being there at all. Thanks for joining me on this explainer. I hope this completely changes how you think about reasoning and execution.